Good afternoon. So, yeah, it's a 3 p.m. is a little difficult for having classes, but I guess we don't have much choice. Okay, so I'll just wait about a minute. Yeah, okay, now it's 3, so we'll get started. Let me share my screen. Okay, so let's get started. So yesterday we were looking at the first class, so to speak, really of the ML course, and we were looking at base classifier, right? So we saw, I mean, I just briefly described to you what are all the properties base classifier enjoys, right? So it is optimal, which we are going to prove in due course. We are going to show that it's actually optimal. And I also briefly described what is the overfitting problem, right? So I hope everybody understands that. So overfitting problem occurs. Uh, yeah. So if I may ask you in the chat, does it occur in noisy case or noiseless case? At least in the example given here, does it happen in the noisy or the noiseless case? Yeah. So in the example given here, at least you observe that the overfitting happens in the noisy case. What I mean by that is, if at all 3 points are actually collinear and you use the Lagrange interpolation formula, then you will get, even though 3 points can potentially fit up to a second degree polynomial, as you can see here, all the second degree terms will cancel out, eventually giving a linear output, right? So this you can try at home. I don't know if you can prove it. Also, that would be nice for a general case, but this actually turns out to be true, right? So, but whenever there is a noise, then we are in a big trouble, right? Because then these kind of things will happen. So this was the example of when there was some noise, even though the underlying relationship between area and price is linear, because there was some noise, and when you try to fit a polynomial, the third degree polynomial may be an extremely bad fit, as you see here. Okay. Yeah. So then finally, after discussing all the properties that the base classifier enjoys, we were actually looking at some examples. Okay. So in particular, we looked at the credit default problem. There were 3 things that we said we will look at. Okay. The first case is there is no information available. Okay. So the second case is we have an indication. The feature is whether or not the person has paid tax on time or did he pay earlier, right? This was the case that we had started. And eventually we will look at time difference between when the person actually paid tax in relation to a reference time. So could somebody say, if somebody is a defaulter, what could be a reasonable assumption here? I mean, should it be a positive value or a negative value in the chat, perhaps? So time when tax paid versus reference time, will it be positive or negative for a defaulting individual in the chat? What do you say?
Positive.
Yeah. Okay. Yeah.
Positive.
Yeah. Good. So that's like, I mean, it need not be true, but I'm just making such assumption just for the sake of, developing this theory, right? So the setup one, we actually did it yesterday completely. We looked at the priors, and we showed one important thing, that whenever there is really no information, by simply adding noise variable z, right? Means by adding some randomness to the classifier, that really doesn't help. So we did show that. So yesterday, a few of you were thinking that this is not true for all values of priors. Has somebody come up with an example where randomness helps? Is there anyone who has come up with an example where randomness helps? I really don't remember who asked that, but Mahendra, was that you who asked me?
Yes, sir.
Did you find out any example?
Sir, I think sometimes randomness do help. Like if we take h of x comma 0 equal to 1, then
you haven't thought of it still. Okay, you write
yeah,
down
I
and
tried. Yeah, I tried, but how do we get the probability of h of x comma 1 not equal to yx? what were those probabilities? I didn't have the notes, so I didn't
Okay.
remember.
Okay, you try it out again today, and next class you please tell me if you are able to find any example. Okay.
Yeah.
Okay, the problem at least is clear. No, you
Yeah, yeah.
define, you should choose P1, P0 in whatever way you like. Show me a case where randomness helps, right? But actually, I can replace this with the algebra. Like you can call this as capital, like some P. This you can call it as some small p or capital P, and then you can show that. See, when you are taking, okay, let me ask everybody this, right? Okay, so what has happened? Why is it not writing? Just a moment. Just a moment. I need to reopen this. Okay, so let me share again. Okay, so see, essentially what I'm saying is there are two numbers, A and B. Okay, and you are trying to do P into A plus 1 minus P into B. Okay, I'm trying to find max of this is like what is a number that is the maximum that you can achieve. Arg max means I'm trying to find the small p belonging to 0 1 such that this happens, right? So if I give you this, what do you say? What is the answer for this? What is the value of p that maximizes this? Mahendra, what is this? What can maximize? See, I'm trying to maximize between, say, A is equal to 50 and B is equal to 100, right? How do I, is it, yeah, so how can I maximize this expression? What value of P maximizes this?
Like at p equal to 0.
Yeah,
It
P
will,
equal to 0 maximizes this when B is greater than A, right?
yeah.
So whenever you are trying to find, this is called as a convex combination. Okay, this is called as a convex combination. Whenever you try to find a convex combination of two numbers, one bigger than the other, you should put all your weight on the bigger number, right? So this particular problem actually boils down to this. You get an expression like this for no matter how you choose your classifier, you'll always have an expression like this. Okay, so you try to work it out and come up with an example, or you try to prove it formally. All right. Okay. So, are there any questions in so far on this base classifier setup? Any questions in general before we move to the new topic? All right. I'm assume no questions. All right. So let's move on then. So we did finish this. So we also concluded that randomness doesn't help, right? So that is what we did. And then finally, yeah. So this is the setup that we are going to start with. So let me just copy this over and then we will start in a new document. Oh, doesn't, oh, okay. Just a minute. It didn't. All right. I think we don't have much choice. What's happening? Just a minute. All right. So yeah. Okay, so let's get started with the same problem, but now we have extra information. So now, right, remember that your classifier, let me use a different color. Classifier is a function from your feature space to 0, 1, right? So now we already saw that randomness doesn't help. So for this particular problem, what do I need to predict? So what is the classifier going to do in this setup? Like what is the output going to be? I will just answer here. So what I need to say is what is the value of h of 0 and what is the value of h of 1. Okay, so if somebody comes to you who is paying early or on time tax, what is it that you should predict whether he will default or not? And if there is another person who does not, who is a late taxpayer, what is it that you would like to predict? So these are the two things that we are going to do. Okay, so before that, let me just briefly explain some of the other new things that has come in here. So you have these are called as priors. Okay, this is the same as before. So P of 0 is what is the probability that y is equal to 0. So what is the probability that the person doesn't default, right? So this we have already seen. And class conditional density, what it is saying is given that you are class 0, okay, what is the probability that the person pays the tax on time, right? So now, yeah. So now the question is how do we go about doing this? How do you estimate this number? So first question to all of you. So let me ask a general question, not this particular thing. So let me ask this question: what is the probability that um, somebody is a left-hander? Okay. So first of all, what is the probability that somebody is a left-hander? This is like a prior, right? How do you estimate this? So if I want you to make a guess here, how will you do this?
It's a very natural thing. Like many people can be left-handed. So the natural instinct says like 0.3, 0.4, because in some cultures it is not accepted. So 0.3, 0.4 is awesome.
Yeah, that's true. But if I were to ask you to estimate, let's say in Goa, what is the proportion of people who are left-handed? If I ask you this question and you don't know, but how will you approach this problem? How do you find out this number?
We'll take samples.
Yeah, you just take,
and count the number of
yes.
people.
Whatever you said is correct, Siddhant. I'm not disputing that. The probability is probably very low. In fact, in some auditoriums, like in auditoriums, there are left-hander and right-hander seats. I don't know if you have noticed, but every 15 seats, there will be one left-hander seat. So I think the proportion is 1:15, something like that. But anyway, how you estimate is you count the number of left-handers in a given population, right? You just do this. So this is how you estimate the proportion of left-handers, right? So this is very, very natural thing to do. So next, if I ask you, what is the proportion of left-handers given that somebody is a male? So how does the problem change? Yes, how will you estimate this?
Intersection, left hand with their male.
No,
Count the
I
number
want
of-
you. I want you to estimate this in the same way how we estimated this by doing some kind of a sampling. So how do you sample for something like this?
We
We
will
will
take
only
the
pick
sample of
males.
males.
Yeah. So you will look at left-handers who are males and males, right? Divided by total male population, right? So this is exactly, I mean, whatever, I don't know who was saying, but the definition somebody told, right? Who was that? I don't know, but somebody told the definition. So that definition is true. I'm not disputing that. But if you have to estimate the conditional probability, it is actually quite, as a matter of understanding this, it's just that you are only interested in the male population. When there is no conditioning, you are interested in the general population. When you condition, you're only interested whenever the conditioning is true, right? So I'm in some sense trying to make you understand how the conditioning is working. Why is it that probability? So if you look at the probability definition, right? So that is what. So can someone tell me what is the probability definition?
Number of favorable outcomes by total number of outcomes.
Yeah, that is correct. But for the in this example of left-hander and male,
L intersection male by male.
Sneha, this is okay, right? You have seen this formula.
Yeah.
Sneha, have you seen this?
Yes, sir.
Yeah. So this is L intersection M by M, right? So see now, can someone make this connection between this and this? I mean, this looks like a completely different thing. This looks like a completely different thing. If you want to intuitively understand how these two are connected, can someone make that connection?
Divide both sides by like total populations, like random.
So yeah, so that is correct. So that is a good way to make the connection. So what you can do is you take this. Okay, this is yeah. So you divide the total side by so left and male divided by total population. Okay, divided by male by total population. Right. So this way you can see the connection. Now this is nothing but left intersection male, and this is nothing but male, right? So conditional probability is not that the definition. This is given typically as a definition, left intersection male, right? This is given as a definition like this, right? So, but the definition is coming from a very simple understanding of this, right? This is the background understanding, okay? So I don't know if this made sense, but yeah, anyway. So now what are we saying here? So that is in the same light. What is the interpretation here? Can someone say what is the meaning when I say this is 0.1? What is it that we are saying here?
Probability that someone pays their taxes late, given that he is not a defaulter.
Yes. So basically, you are only interested in somebody who is not a defaulter. And given that somebody is not a defaulter, you are only looking at what proportion of them are paying taxes on time. Okay, that is very good. So that is exactly what it is. So now one question to you. Yeah. So should this sum to 1?
No, sir.
No, sir.
Okay. So answer is no. Yeah, good. That is correct. Okay. So what actually? So I mean, how about this f0 of 1 plus f0 of 0? Is this 1?
Yes, sir.
Yes, sir.
Okay. So can someone tell me why?
Because given y,
Yeah. Yeah. Go ahead.
for a given y, x can have only two values, 1 or 0. So
Yeah.
probability is with that.
Yeah. So for a given y, when you fix y equal to 0, right? So this is nothing but p of x equal to 1 given y is equal to 0 plus p of x is equal to 0 given y equal to 1, right? So given y equal to 0, sorry. So given that y is equal to 0, there are only two possibilities for x. Either it can be 0 or 1. So this two should sum to 1. Okay. So yeah. So the point of just explaining this again is to make everyone recollect what is it that it means to say this conditional probability and so on, right? So I wanted you to understand that very clearly. Okay. All right. So now let's just move on. So let's write whatever is known for setup. So we are now in setup 2 still. We haven't given you the base classifier yet, right? We haven't seen it. So let's see what is there in the setup 2. You have priors. So P0 and P1. Okay, this is probability that y is equal to 0. This is equal to 0.9. Did we choose that? 0.9. And P1 y equal to 1, which is 0.1. Then we have class conditional densities. Okay, so this is the name given, conditional densities. Okay, even yeah. So that is f0 of f0 of what was the number I gave? f0 of 1, right? f0 of 1 that is equal to probability that x is equal to 1 given y is equal to 0. This is equal to 0.1 and 0.95. 0.1 for this, and f1 of 1. Okay, so that is 0.95. Okay, so these are all the things given to us, and what we need is the base classifier, which gives what I should report when I get 0 and what I should report for when I give 1. When somebody is what is 0 stands for? Let me just get that clear. 0 is early or on-time taxpayer. So 1 means late, right? So when somebody is a late taxpayer, what do you predict whether he's going to default or not? And when somebody is not a late taxpayer, what do you do? So this is the question. Okay. So now, so this is now a question that is answered by what is called as base rule. So let us again recollect that. Okay. So base rule. So let's try to intuitively redefine, re-arrive at base rule, and then I will give you the definition that is generally taught, and hopefully that will be a good reminder for everybody, right? So what I'm interested is, suppose x is equal to 0, right? I am telling you that x is equal to 0. Somebody is a on-time taxpayer. You are interested to find what is the probability that this person will default given x is equal to 0, right? So we are having what we are having. We are having this, right? We are having okay. So this is what we would like to find. What we have is what we have means very similar to this. We have another quantity which is probability that x is equal to 0 given y is equal to 1, right? So what is this number in the chat? Can someone tell me what is this number?
0.05.
Okay, so this is 0.05. Now, is probability y equal to 1 given x is equal to 0 same as this?
No.
No, right? So so it's kind of very easy to understand that, but let's try to derive it from first principles, how you think about it. Okay, so let us try to first do this, right? Very informal discussion first, and then we will come to the formal discussion. So informally, what we are interested is, you look at so y equal to 1 means defaulters who pay
Taxes early or on time.
early tax. Yeah, so that's what we are interested in. Defaulters who pay early tax divided by people who pay early tax. Okay, this is what is the definition, right? So now denominator, we can write this as, so let me copy a few things so that we just don't waste a lot of time. Let me write again. Defaulters who pay early tax divided by so all the early taxpayers are coming from two categories. What are those?
Who defaulted and did not default.
Exactly, right? So we will have first quantity is defaulters who pay early tax plus not defaulters, right? Not defaulters who pay early tax. Okay, so now let me ask in the chat if this is clear to everybody. Yes? Do you understand this so far, whatever I have written? Informal stuff? Okay, very good. All right, so that is nice. So now what we will do is, assuming that there are, okay, so now we have to be a little careful. So let us try to estimate each of this quantity one by one. Okay, so let's copy this somewhere and try to estimate each of this quantity and rederive the base rule. See, base rule is such an important concept, and sometimes people don't understand it and they remember the formula. For remembering formula is okay, but you should also understand it, right? So that's why I'm spending some time going after this. So this is informally, okay. This is not, yeah. So this is what we would like to find out, right? So let's try to do this step by step, okay. Defaulters who pay early tax, okay. So if I want to estimate this, so let's say total number of defaulters is ND. Right, this is the total number of defaulters. How do I estimate what proportion of these are going to be defaulters who pay early tax? Can someone tell me?
So we can take the intersection of people who default and who pay tax early.
Yeah, that is correct. But I am telling you, suppose ND is the number of people who have defaulted. Okay, so out of that, how many will be early taxpayers? I mean,
Total, we will divide by total taxpayers. Total early taxpayers.
no, right? So I mean, defaulters who pay early tax, like you are not interested in all the people who are paying early tax. Okay, let me ask this way. Okay, so let us say that every day probability of rain is 0.1. Okay, so probability of rain is 0.01, let's say. Okay, so what is the number? How many days do you think it will rain in any year?
3 days, 3.65. It's multiplying with the
Yeah, so 300 into this. Yeah,
Yes.
exactly. 3.65, right? Roughly, you can estimate like that. So if the number of days that you're looking year, yeah, 3.65 is not really good because there is a 0.65. But assuming that this error we are okay to live with, right? So defaulters who pay taxes, this ND is like the number of days. So what should I multiply it with?
Probability
Probability
of
of
defaulter
early.
given.
Yes, very good. So that is what I would like to multiply it with, right? So what is that? That is nothing but this guy, this quantity, right? X is equal to 0 given y is equal to 1. Okay. All right. So this is one thing. Okay, so this is one thing, and if I want to estimate this even better, how can so total number of population is n. So what is ND? How do I get ND?
From priors. So
Yes. Yeah. So probability that y is equal to 1. Okay. So do you see what I'm trying to do? So this is this, and what about the second term? Yeah, so this is probability of non-defaulters into what should I do here?
Probability of x equal to 0 given y equal to 0.
Yes, so that is what we are doing, and as before we can also write this as n into p y is equal to 0 into p x is equal to 0 given y is equal to 0. Okay, so now we have the base rule, right? So you can see that. So now if I put everything here, this capital N gets cancelled out throughout, right? So this is not really a proof really, but I'm just trying to show you the intuition how it is coming. Okay. So let us just write this and finally write the base rule directly. So what is that? So probability that, what is it that I was trying to compute? Y is equal to 1 given x is equal to 0. So this is going to be, so you can see, so p y is equal to 1 into p x is equal to 0 given y is equal to 1 divided by y equal to 1, p x is equal to 0 given y is equal to 1 plus p y is equal to 0 into p x is equal to 0 given y is equal to 1. Okay.
So y equal to 0 in the last.
Yeah, sorry. Okay, so this is what we have. Okay, so and this is the posterior. Okay, and we write this as yeah. So we can write this as P1, and this number is F1 P1 F1, right? P1 F1 of x is equal to 0. X is equal to 0. P1 F1 of 0 divided by P1 F1 of 0 plus P0 F0 of 0. Okay, and this number is also sometimes written as Q1 of 0. Okay, so yeah, so basically we have the posterior computation. What we do is we just say Q1 is Q1x, whatever value of x you are interested in is nothing but P1 F1 of x divided by P1 F1 of x plus P0 F0 of x. So that way you can get. So x takes two values. X can be either 0 or 1. So you can use the same formula. Okay. All right. So now, given that we have computed the posterior, what do you think should be the base classifier doing? So now we have computed. Let's just compute the values. Okay. So let us compute Q0. See, this notation gets a little tricky. Okay. So just you have to be a little careful with that. Other than that, everything is okay. So Q0 of 0, what is the meaning of this? This is the probability that, okay. So this fellow comes here, y is equal to 0 given x is equal to 0. Okay. So let's put in the numbers and compute this. Can someone do it? So let's look at the values from up here. P0 is 0.9. Okay. And F0 of 0 is 0.9. So this is going to be 0.9 into 0.9 divided by 0.9 into 0.9 plus P1. P1 is 0.1 and F1 is F1 of 0 is what we are asking, right? So F1 of 0 is 0.05, I think. F1 of 0 is 0.05. So what is that? So you will get 0.81 divided by
815.
6. Huh?
Yeah, it's around 0.99.
Yeah. Oh, 0.81. Okay. So I think 0.81 by 0.815, it's close to 0.99, I think, right?
Yes, sir.
Yeah. Okay. So this is what some approximately, let's say it is equal to approximately 0.99. So now what should be the base classifier doing? HB of 0. So it's
Responding according to the max posterior probability. Yeah.
Sorry.
So if it's 0.99, then it should give y equal to 0. So
yeah,
it should return 0.
0. It should return 0. Okay, so that is what it is. So it will give 0. And in the same way, let's try to do for the other one. So Q. So now we are interested in Q0 of. So now we are interested in x equal to 1, and we will ask what is the probability that it came from y equal to 0, right? So what is probability y is equal to 0 given x is equal to 1? The same way. So P0 is same 0.9, and now we are looking at F0 is probability that x is equal to 1 given, so F0 of 1, right? So that is what we are having here, F0 of 1. F0 of 1 is somewhere here. See, this notation is kind of confusing, but if you forget the notation, it is actually very simple. Maybe for the time being, you don't worry about the notation, directly use the base rule. Okay. So let's try to do that without worrying about this. So this is equal to probability that y is equal to 0, x is equal to 1, right? So that is equal to probability of y equal to 0, which is 0.9 into x is equal to 1 given y equal to 0, x is equal to 1 given y is equal to 0. That we said was very low probability. What is that?
0.1.
0.1. And 0.9 into 0.1 plus you're trying to do x is equal to 1, right? Denominator is probability of x is equal to 1. So y can be 1 and x can be 0. Y can be 1 is 0.1. And what is the probability that x is equal to 1 given y is equal to 1? X is equal to 1 given
0.95.
0.95. Okay, so thank you. So doing the computation, so this will be 0.09, this will be 0.09 plus, let us say, approximately 0.0, not approximately, exactly 0.095. This is some number, what is this? 0.48.
Probability is 0.48.
0.48. Okay, so Q0 of 1 is this. And what about if Q0 of 1 is this, what is Q1 of 1? This is just the sum, it sums to 1.
0.52.
Yeah, 0.52. Okay. So, yeah. So you will, in this case, you will report 1. Okay. So base classifier HB of 1 will report 1. Okay. So this is what the base classifier will do. Okay. So let me just pause here and see if anyone has any question. Is this clear so far? Okay. So a little bit of this notation is what might be a little bit bothering you, but that should be okay. You'll get familiar with it. All right. So then we haven't seen so far any proof of optimality. At some point, I will prove all of these things are optimal. But let us for now move into the third case. Okay. So setup 3. So now your feature x will be a number between minus infinity to infinity. What I will further assume is that this x is actually representing a quantity which is time when tax paid minus reference date. Okay, so that's what we will assume. So this is this. So the original thing still remains. P0 is 0.1 and P1 is 0.9. Okay, this was the original setup. This is original, right? So just for the sake of this particular development that I'm going to talk about for next 15-20 minutes, I will make a small change here just so that things become, algebra becomes easy, and then we will come back to the original setup. Okay, so this is just a temporary assumption. What I will do is I will assume that these are equal probability. You will see why this is going to be helpful initially. Afterwards, it's fine. Afterwards, you will understand it's not that big deal. So that time it will be clear. Okay. So for the time being, I will assume that these two classes are having the same prior. Okay. Now, given that these are the priors, I need to assume the distribution. So of x. Okay. So I need to know how does x change? What is F0 of x? Okay, so when somebody is paying the taxes, when somebody is not defaulting, I want to know how does the x look. Okay, so that is 1. So this is remember this this is what we said earlier. Earlier, since you were in the discrete world, right? In the discrete case, we had PMF, probability mass function, right? So we were able to represent F0 of 1 as probability that x is equal to 1 given y is equal to 0. So this was the PMF in the discrete case. So what is it that we should change this to the continuous case? If I want to change it, what is it that I need to do?
Less than equal to.
Less than equal to.
Less
Yeah,
than
yeah,
equal
yeah,
to.
yeah. That you can either go to CDF, that is correct. You can do that, or you can look
Density
at
function.
yeah, you can look at probability density function. Okay, so let's look at the density function because that is useful for me in this case. So let's assume that whenever somebody is paying the taxes on time, right, it has a normal distribution. So this is, let's say, F0 of x. Okay, so this is x. And now on the same axis, so this number where it centers, let me assume this is as -1, right? See, if somebody is not defaulting, there is a good chance that they will pay early, right? So the number will be negative. Okay, so let's assume that F0x has a distribution normal with mean -1 and variance sigma squared. Okay, so this is one assumption I will make. And for the other case, let us assume that that one is actually, there will be late, right? So if somebody else is, if I look at f1 of x, somebody who is defaulting, there is a good chance that they will pay later than the reference date, right? So you will have something like this. So these two shapes, let me for the time being assume that they are the same. So this is normal with mean 1 and variance sigma squared. So this is what we have. Okay, these both, though they don't look very similar, let's assume that they are the same shape. Okay. So just for the recap, can someone tell me what is the normal distribution? So if there is a normal distribution with mean mu and variance sigma squared, what is the density? Suppose x is normally distributed. So what is the density fx? The formula? Sneha, do you remember from electrical? Like, did you see this? I mean, you should have seen because it comes all the time in your communication systems.
So 1 by root 2 pi sigma square.
Yeah. Okay.
E power minus mu by sigma the whole square.
Yeah.
By half.
Yeah. Is this okay? Yes. So what that happen? So there are two parameters that govern it. So mu represents the center, the mass. So this mu is here is -1. Here mu is 1. Sigma square represents the spread. Okay. So that is the variance. All right. So I hope everyone remembers a little bit things about normal distribution. Okay. So this is given to us. Now, okay, so now what we need to do is we need to think of what is the probability that, so we are interested in the posterior, right? So what is the probability that y is equal to 1 given that x has taken a particular value x? So this is what we want to find out. So let's use the base rule as before. Okay, so let's write this as P of y is equal to 1 into P of x is equal to x given, yeah, y is equal to 1, all right, divided by okay, so this actually becomes P0. This is nothing but this is numerator is P1 F1 of x small x divided by P1 F1 of small x plus P0 F0 of small x. Okay, so this is how it will be, and this quantity is nothing but Q1 of X. Okay, what is the probability here? So one question. Let me just try to explain this formula a little bit, right? So this formula needs a slight justification. What is the problem here? Can someone tell me any issues that you see in this formula?
We can't use probabilities here. We should use densities instead.
Yeah. So I have actually changed into densities, right? F0 and F1 are now densities, and I have put F0 and F1, right?
Okay, I mean in the above formula.
In this, yeah. So in this formula, yeah. So what is it? Okay. Somebody can one. Yeah, one of you, can you tell? There were 2-3 noises I heard.
In that formula, we'll get 0 by 0 if we write just.
Yeah. So yeah. So basically, if I take a continuous distribution, right? So let me just small recap, right? So when you have a continuous distribution, if I ask you, so let's say some Z is normally distributed with mean 0 and variance 1, right? If I ask you what is probability Z is equal to some value, let us say 0.1, this is always 0, right? I hope everybody remembers this.
So we need to integrate in the denominator, because we can't just use a point. We can't just calculate at a point the density function. We need to integrate it.
Yes. So that is yes. So but if I integrate on a single point, I will still get 0, right?
Yes, sir.
Yeah. So what we are doing here, yeah. So you're right. So that's correct. So instead, what we will say is like instead of trying to compute posterior in this way, what we will do is we will say probability that y is equal to 1 into probability that x is equal to x, given that so yeah, this is the problematic guy, right? So instead of saying probability x is equal to x, I will say x belongs to x small x minus delta by 2, comma small x plus delta by 2, given y is equal to 1. Nikhil, is this okay now if you use something like this?
Yes, sir.
Because now that you have a interval, it's no longer the case that it will be x0, right? So the same, let me write here, x belongs to x minus delta by 2 into x plus delta by 2, given y is equal to 1, plus p y is equal to 0 into x. I'm just not writing this, okay? You can just write the rest of it, but it's fine. So now how does that help? Can someone tell me from here, how do I go to this formula?
We can assume like the distribution to be constant during that interval.
Yes. I hope everybody remembers that. So whenever you have a density, if I take a point and if I take a very, very narrow strip of width delta, right? Suppose if I take this as width as delta, and suppose this is the point x, then I can say probability that x belongs to that strip is equal to f of x, approximately f of x times delta, right? So that way now we can directly put this as P1 F1 times delta divided by P1 F1 times delta plus P0 F0 times delta. So all the deltas cancel away. Okay. Is that all right? So is this formula now meaningful? Even though we wrote it this way, it is still well defined. So this is the posterior. Okay. Does anyone have any questions here? Okay, so very good. So now that we have defined the posteriors, so what should the base classifier do? So for a given, so how do I come up with HB of x, small x? So what is it going to be?
So 0 or 1 depending on Q0, Q1 values.
Yes. Okay. So this is going to be indicator function. You're right. Whatever you said is correct, but I will just write it this way. So indicator that Q1 of x is greater than or equal to Q0 of x. So what is an indicator function? So indicator function will be 1 whenever this condition is true. Okay. So if Q1x is greater than Q0x, then HB of X will be 1. If it is not, then it will be 0, right? So that is the way we will do. If you don't like this very much, so we will say HB of X is equal to 1 when Q1X is greater than or equal to Q0 of X. Okay, 0 when Q1 of X is less than Q0 of X. Okay, so this is going to be the base classifier. So let's try to, so now, so let's try to analyze this. So we know what is Q1 and Q0. So Q1X is nothing but P1 F1 divided by P0 F0 plus P1 F1. Okay, so this is greater than, suppose if it is greater than P0 F0 by P0 F0 plus P1 F1, right? So now remember, I said that just for the sake of ease, I have assumed that P0 and P1 are same probability, right? I have made this assumption. So can we simplify this and make it little simplifications can we do? So one thing we can do is all of this will get cancelled. These two will get cancelled. So what we are left with is F1 of X, whenever is greater than F0 of X, I am going to report 1. Okay. And so if I do further simplification, see, I have assumed that this is normal with mean 1 and variance sigma squared. This is normal with mean -1 and this is sigma squared. Same variance I have assumed. So you know the formula, everything starts getting cancelled. And intuitively, without even trying to do this properly, if I just go back to this shape, right? Let me copy this over. Okay, I lost the, didn't copy properly. Just a minute. Okay. So these regions are given to us. So can someone tell me which region I'm going to report 0 and which region I'm going to report 1?
Yeah, at the intersection like 0, left than 0, we will predict red, and right we will.
Yeah. So this entire region, right? We will this entire region. The base classifier will say this is going to be. So this region is going to be predict
0.
Predict 0. Yes, and this region will be predict 1. Okay, this is true only because I assumed that both the priors are half. Okay, I just did this because you can then easily visualize this, right? So that is what it is. Okay, so this is good. Maybe I don't try. So in the next class, we will try to prove the optimality, which is the next class is tomorrow. I will try to show the optimality of this, maybe, and then we will generalize it for cases where P0, P1 are different multi-class, and we'll finish the base classifier. Okay, and then I will give you an assignment to implement this and so on. But yeah, so let's do that next class. So before that, are there any questions which someone wants to ask? Okay, then. So let's stop here. I will just hang back if any of you have any questions. Okay. So thanks, everyone.
Thank you, sir.
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 Bye, sir.
Sir, for multi